So introduction to robotics is past, present, and future. So there is a lot of talk of robotics. This word robot is used extensively. Okay, and you look at TV, you look at newspapers. There is always something or the other to do with robotics. Okay, now it's very interesting to note that when somebody uses the word robot, or when you read the robot or the word robot somewhere, what is it that first comes to your mind? Okay, somebody said, this is a robot, I work in robotics, or I'm interested in robot, or I have made this robot, please have a look. So what comes to your mind first when you think of robots? Okay, each of us has a different perception. Okay, so some people will think that they are mechanical machines. Okay, some would think that they are companions, friends. Okay, some will think that they are pets and toys like this. Some would even say helpers. Some will say dangerous machines. Okay, so maybe all of this would come to your mind. Okay, but certainly something will come to your mind. Okay, and it's very interesting to note that as time has progressed, our concept of robotics has also moved in this direction. Actually, it has also evolved. Okay, 1960s, 1970s, there are mechanical machines doing jobs in industries. Then little bit more advanced, we have robots which are friends, companions. You have robots today in other areas also. Okay, social robotics, so companions, friends, pets, toys, helpers. May not be so much in India, but in other countries, helpers are already there. Okay, rehabilitation, helpers. Then this is another one which is becoming very common, dangerous machines. Okay, for example, automatic weapons, okay, drones. These are all robots, and they are dangerous machines. So depending on what you're thinking of robots, something will come to your mind. Okay. Now this business of robots have moved on from the past, present, and future. Why this important is past is where it came from, or this is industrial robotics, which is about 1960s, 1970s. Robots, a lot of robots doing a particular task in an industry like automobile industry or electronics industry. So this is the past. Okay, robots were essentially used to replace human muscular power in industries. And then this is the present. Okay, so so the present is okay. Unfortunately, the video is not playing, but anyway. So the present is basically Amazon. Okay, you might have seen the video. Okay, so in Amazon robotics, there are robots which are used almost everywhere. Okay, right from material handling to So I insisted on showing this video. Okay, because this actually shows that we are actually connected to robotics in almost every way. Okay, we might think that robotics, we have nothing to do with robotics, and robotics is just some kind of a subject somewhere. But if you look at Amazon today, okay, you look at most online retail services, Amazon, Flipkart, others, okay, which we are using. Okay, all of you would have used Amazon or Flipkart or whichever way. Now the material handling in this automated online retailing is completely automated. Okay, and this is something which is there. This is the present, and this is also the future of retail. Okay, so we are all connected. When you buy something on Amazon, you place an order. The order is processed automatically, and then from wherever the part has been placed or the product has been placed, it is retrieved automatically by using a robot, and then it is dispatched to you. Okay, the full process is automated, and this is where we talk about robotics in terms of motion planning, in terms of material resources, material planning, then delivery. Okay, now this has to do with mobile robots. Okay, it has to do with motion planning. Now you can look at the design of the robot, which is essentially retrieving the part. Motion planning, there are about 3,000 robots which are working simultaneously. Okay, now if there are 3,000 robots working simultaneously, then how are you going to do the motion planning? Okay, and obviously it has to be the fastest. Okay, you have to have a plan such that the robots don't hit each other, and it must give you the fastest delivery time. Okay, so this is something which we feel that we may not be connected to robotics, but we are in a way connected, because the product that is coming to you is actually being automated and being given to you. Okay, now in terms of retailing, this is the future of retail. So what the human being will do, the human being will only do that. Okay, so he'll take the part, put it in the packet, and give it to you. Okay, the rest of it is completely automated. Okay? This is the future of retail. Okay? And this is the present, and it's likely to be the future also. So we are all connected to robotics in some way. Okay? We don't see it directly, but it's already there. So I insisted on showing the video because this at least convinces people that, yes, that we are connected to robots, and this is the way forward. So the past was this, the present is this, Amazon, retail, et cetera, Now, in terms of future, many countries it is already there, concepts like social robots, right? So robots living in society, where in rehabilitation, healthcare, hospitals, in airports, giving directions, et cetera, helpers, teachers. Okay, these are already there in so many. So this is the future. This is probably the direction in which robotics is going to go. Okay, so from industrial applications to online retail to the direction of social robotics, where robots are actually going to come and live in society. Now, so essentially robotics is not only a question of looking at kinematics, dynamics, control, motion planning. Okay, other aspects of things like behavior, okay, has also come inside. Okay, what should the robot look like you? Should the robot not look like you? Should the robot look like a human? Should not look like a human? Okay, should it behave like a human? Not like a human? Which things were not there before? It's there today. So in robotics, all kinds of people have got involved. Apart from the engineers, we have people from social sciences, we have people from humanities, we have people from psychology. Okay, so everybody is included in robotics today. So robotics actually has become a very, very large discipline by itself. Okay, and that is the direction in which it is going. A lot of interesting questions have come up, okay, which never existed before, but which are there today. For example, when you think about a robot, what will be the gender of the robot? Will it be a male? Will it be a female? Will it be neutral? Okay, these questions did not make any sense, say, 20 years ago. But today it makes sense, because if there is a robot, you're going to buy a robot is going to be there in the airport or in the hospital, then what should be the gender of that? Okay, will this ever come to your mind? So these kind of things make sense today, which were not there before, right? So this discipline is progressing, and it is likely to go for the next 20 to 30 years at least, where we are going to automate a lot of services and industries. So what we like to know here is, in terms of teaching, okay, we should be very clear that where robotics came from, where robotics is going, and what is the future of robotics. Okay, so what we'll be trying to cover is, where did robots come from, where we are in terms of robotics, and where robotics is going. Okay, why we should know this? Essentially because when you're doing research, you should be very, very clear that what is the research in the next 10 years or 20 years. Okay, so starting off from the very basics of this course, that is the origin of automation. So robotics is a part of automation. And what is automation? Again, these are terms we use very, very commonly. So when we say automation, what is automation? If somebody asks you, you're saying automation, home automation, industrial automation, what is this automation? Okay. So the definition of automation is essentially replacing human muscular power. Okay. So robotics is a part of automation, and automation is the process of replacing human muscular power. Okay, so we can have office automation, we can have home automation, you can have all kinds of industrial automation. Okay, today we have retail automation. So the objective is essentially replacement of human muscular power, and this business of automation has been going on for thousands of years. It is not that anybody invented automation. Okay, this is a process which started off very long ago. For example, 10,000 BC, in the early days, human beings used different kind of tools. So we had copper tools, stone tools. Initially it was stone tools. Then we had iron, then copper, in that order, right? So tools make better tools. In terms of the future, we can say that machine tools make better machine tools. So we have the NC machine, then we have the CNC machine, then we have the DNC machine, in that order. Okay? So tools make better tools is a philosophical statement, but actually tools make better tools, and that is how human civilization is progressing. Tools are making better tools. Okay? So this is very long ago, 10,000 BC. We move on a little bit more. Design of simple automation was there around 150 BC. So this is still BC, so this is very long ago. Now, simple automation like the moving engine. So this is the earliest example of a steam engine. Okay? So a steam engine, there is a bucket of water, and it is covered like this with two pipes going out to this hemisphere, and the steam coming out in this direction and this direction, right? So how this works is essentially they would burn fire here, which will heat the water and produce steam. The steam will come out from this direction, from this pipe and that pipe. And because they're in different directions, there will be a resultant moment about this axis. Okay? And this is the earliest example of a steam engine. Okay? So the steam engine was not invented by James Watt, okay, as claimed. The steam engine has always been around for a very, very long time. Okay? It is only James Watt put it to that locomotive, and then he used it like that. Okay? So the story goes that 150 BC, the Greeks were actually using this kind of devices for doing automatic tasks. This is another automatic opening, closing of doors. So how it works is almost same as principle of working is similar to this. So they would burn fire here. And if you burn fire, what will happen? The pressure here will go up. The pressure here increases. It will force the water down. So the water will go through this pipe and go in there. And if the mass of water increases here, it will pull this down. This is connected to a pulley, which will rotate. And if it rotates, this door will open. Okay? And you have automatic opening of door. Okay? So they would burn fire here. This door will open. They'll put out the fire. The pressure will go down. The water will flow backwards. And the door will close. So opening, closing, automatic device using steam power. But if you look at the date, it's 150 BC. Okay? So automation has been around for a very long time. And automation is a process by which tools are making better tools to replace human muscular power. Now, whenever we talk about automation and such things, we always tend to say that the Greeks did this and the Greeks did that. Okay? Now, probably in India also we have different kinds of automation, or we had, but we don't have records, so we don't know. Okay? But in India also probably we had different kinds of automation, automatic devices which were being used for thousands of years. Okay? Now, this is 10,000 BC, 150 BC. This is about 1780. So the creation of automatic dolls which could write and draw pictures. Okay? So these are some of the dolls which are still there in some of the robotics museums worldwide. Okay? They are simple mechanisms which can do something. Say, draw a picture. Okay? So this is essentially a mechanism, but 1780. 1800, in terms of progress, we saw the manufacture or the design of automatic power looms in France. For example, this gentleman called James Jacquard, he invented the first textile machine, or the program textile loom for design and manufacture of textiles. Okay, that is clothes. Even today, we use this kind of a device for when the weaver weaves. Okay, you would have seen there is a structure like this, and there are threads which go in this direction, and there are threads which come from the top. So how does the weaver actually make the design? So by changing the position of the threads which are coming down, okay, the person makes the design in the cloth. So this is the way it is done even today. Okay, you would have seen on TV very often. So there is a bar like this, and the person holds the bar and pulls it down, changing the position of the threads, and that makes the design on the cloth. Okay? So what this gentleman did is that he embedded the design that was to be made on the cloth in the form of a program which he wrote in a punch card. So this punch card is something similar to our OMR sheets of today. Okay? So in this punch card, there would be lines, and each line will have circles. So there is a hole or there is a no hole. Okay? And there would be a reader which can read that. So if there is a hole, probably it means 0. If there is no hole, it means 1. Okay? Either way. And this is something similar to the cards we use today, where the OMR sheets, where you make a circle, you make it black, or you don't make it black. And there's the reader which reads that. Right? So the program which was made for having this textile, making the design on the textile, was written in the form of a program, in the form of a punch card. And this machine could reach the punch card and correspondingly change the position of the threads. Okay? Now this is the earliest example of a program device. And the early machines, computers and NC machines, also use this punch card. Okay? The earlier days. So in terms of program, the earliest example is probably around here, 1801, in the form of textile machines. Now we move on further. 1904, essentially, there was an idea of using transfer lines. First came out in the Ford Motor Company in the US, 1904. Okay? So what we are trying to see is historically how this subject of automation has changed, and where did robotics come from. Okay? So this is all hard automation till now. 1904, Henry Ford's mass production of vehicles in the US, and even today we use this the concept of transfer lines. So there is a conveyor, there is a car which sits on the conveyor and it moves from station to station. Every station, a human being or a robot will do something, and then the car moves on. So the idea of a transfer line was 1904. Now, historically speaking, where did the word robot actually come from and the word robotics? You will be familiar of this, that the word robot first came about or was first used by this gentleman called Karl Kapek, where he wrote a play, 1921, where he said that in future, this is supposed to be a picture from his play, what he proposed, that in future there will be mechanical men who will be replacing human beings to do dirty jobs in industries. And he basically called them mechanical men or slave men. Okay? So 1921, the word robot was first used, and it basically means mechanical men or slaves in Czechoslovakian language. Okay? So the word robot was used 1921 to depict this kind of a device which will replace human beings in future. Of course, there are no robots in 1921. 1942. So 1921, 1942, Isaac Asimov first used the word robotics. Okay? So we are seeing that how automation progressed. And then this word robot was used, 1921. And then we had the word robotics, which was used 1942 by Isaac Asimov. So there are a lot of books, there are a lot of science fiction books, a lot of movies. Okay? I don't know how many of you have seen. Anybody has seen or read any of the movies of Isaac Asimov? iRobot is there. There are so many of them. Okay? Now, he is the person who actually said that in future there will be a subject called robotics, and he also wrote a lot of science fiction for the next 200, 300 years. Okay, what is likely to happen. Okay? And it's very interesting. Well, it's not very interesting. In a way interesting, that a lot of the things he said are coming true. Okay? That is the interesting part, that 1942 there was no robot. That this fellow could imagine that in future there is going to be things like this, and there will be a subject called robotics, and you'll sit here and you'll study robotics. Okay? So that is the interesting part. The more interesting part is that a lot of the things he has said are true. For example, social robots. Nobody could imagine this time that robots will actually live in society with human beings, which is happening today. Okay? A lot of the things he said are scary. They are scary because he said that in 200 years, maybe the robots will take over. Okay? That's the scary part. So it's interesting if you look at, if you watch some of his movies. Okay? There are a lot of them. Read some of the books. Okay? A lot of the things he said are there already, and some of it is likely to come. Okay? Just when we are at this, when we are talking of this, okay, we have robots and Isaac Asimov with his robotics. Okay? There was another gentleman who is very famous. He passed away last year, I think, okay, called Stephen Hawking. Okay? So about 20 years ago, Stephen Hawking said that what is the biggest danger to mankind? So 20 years ago, he said that these aliens are the biggest danger to mankind. Okay, because at that time they were trying to make contact with extraterrestrials and all that, right? And why he said that is essentially because if you make contact and you don't know what is going to happen. Okay? So he had said 20 years ago, which is very famous, that if you make contact, you'll be very happy, but then they might come for lunch, and you are their lunch. Okay? So that is 20 years ago. But just before he died, about 2 years ago, he revised that. And then he said that something is now there is something which is more a danger to mankind. What is that? He said AI. He said that AI is probably the biggest danger to mankind, because the way it is progressing, okay, programs generate more programs, okay, and the person who created the program does not understand what it was made for or what is happening. Okay? So if it continues like that, then probably there is a danger of something going. And that is interesting because Isaac Asimov actually said the same thing. But he said it 200 years from now, that not only AI, but robotics also will take over at some point of time. So let's hope it doesn't happen. Okay? But it's interesting to know that such thoughts are there. Okay? And they have been told even from times where there were no robots. Now, 1942, the first word, the term robotics is used. 1945. So till 1942, there was no robots, of course. So where did the robot actually come from? So 1945, we have during the Second World War, there was a need for making devices which can handle material at a distance. For example, during the atom bomb project, when they were making the atom bomb, what they found is that because of handling radioactive material, they had to make a device by which they could manipulate this material at a distance, or telemanipulation. So this is a device which is called a master-slave manipulator. And it is made such that there are some joints there, okay? And this is placed in the hot cell, which is at a distant location with the radioactive material. This is placed at a distant, quite a distance. So maybe at least there would be a gap of 10 to 15 meters between them. And there would be heavy shielding, either brick wall or other kind of concrete, and there would be a small hole by which the person from here can see that side, okay? And it could do very simple motions. How does it work? There are joints, and these joints are connected by wire ropes and pulleys. From this joint is connected this way to the other joint there. So the master is the person where the operator stands. So the operator will stand here. He will hold this and move in particular direction. So if you move it this side, what will happen? The tension on this cable will change. The tension will be propagated on this side, and this joint will also move. So whatever is done this side is replicated on that side. Very simple motions. Just move, maybe catch something, put it somewhere. It could not do very complex motions. What is a complex motion? For example, moving an object like this is complex. So it can't do that. But it can simply catch something, put it somewhere, pour some liquid, that it can do. Something to note here is that this is a mechanical device. Okay, so the motion transmission is by means of wire ropes and pulleys. Okay, so essentially the motion from here goes like this to the corresponding joint on the other side, and the transfer is by means of wire ropes and pulleys. So there is no program here, there is no electronics, no sensor, actuator, nothing, no program. Okay, so this is the father of the robot, 1945, which is called a master-slave manipulator. And even today, in most of the places where they have atomic energy establishments in India or abroad, they still use this, okay, for handling radioactive material. So this gentleman is called the father of the robot, and something to note is that it is essentially a mechanical device. There is no program, no nothing, force motion transmitted by wire ropes and pulleys. So where did the robot come from? Now, what we are trying to see is that technology has progressed in particular steps, okay, in stages. So in terms of robotics, there are three main stages that happened, three main inventions. Okay, what are these three? Okay, so the first one, which changed everything, is the invention of the transistor, 1948-49. Okay, so before this, everything is mechanical automation. Okay, there is no program, actuator, sensor, and there is no reprogram. So you cannot reprogram a mechanical device, okay, like a master slave. But once you had the transistor, from the transistor we ended up by making the computer, then the microcontroller, microprocessor, in that order. Okay, so basically what we see is that the first major change that came about in terms of technology is the invention of the transistor 1949. And with that came about the concept of reprogram. You could reprogram a device to do something. Okay? So from here, the first robot was made called Shaky at Stanford University, which is a mobile robot. It could simply move around, avoid obstacles. Okay? So because of the invention of the transistor, we have the microcontroller, and with that we could reprogram a device. And 1950, the first robot was created called Shaky. 1952, George Dowell, essentially he filed a patent for teach and playback devices for NC machines and robots. Okay, so NC machines and robots NC machines and robots are essentially having the same technology. What I mean is that they all come from microcontrollers only. So the control system of an NC machine and that of a robot is essentially the same. There's no difference. Okay, NC machine means numerical control, which means control using numbers. Okay, a robot also you're controlling using numbers only. The only difference is a robot arm moves around, you give coordinates, position coordinates. In an NC machine, you say that tool moves X, Y, Z in particular direction, but it's numbers. And the technology is essentially from here only. It's a microcontroller based. Okay, so the feed. No, but you are using another term called thinking power now. So this is not only for see, this is not only for robotics, it's a general definition. Like if you say automation, automation is replacement of human muscular power. It is not only in industry, it can be home automation, office automation, wherever. So it's a general definition. So here also it's a general definition. What is intelligence? What do you mean by that? Yeah, so in a way, yes. So intelligence essentially means ability to deal with unknown, unforeseen, or corrupted data. So if I say x plus y is z, I give x, and now I ask what is z without giving y. Okay? So if it's a normal program, it will not be able to do. But if it's an intelligent program, okay, it can actually find out for different values of y, what is the bounds on z, this side, and say that if your x is within this bound, then your z is that one, depending on whatever you wanted. Now in robotics, this is very important. Why? Because in the real world, most of the data that we get, some sensory input output, will either be corrupted or there is going to be noise or it will be wrong. In the real world, there is no real, there is no exact. So there is always going to be some kind of error coming in with your data, right? So the ability to deal with unknown, unforeseen, or corrupted data is what is basically we define by intelligent system. Okay? So suppose we have a mobile robot which has say 10 sensors in front. Very often out of those 10 sensors, some of them will give wrong result or they will give bad result. They will always do that. It's in the real world. Okay? So using that, can it make sense out of whatever information it is getting? Okay? So a system which can deal with unknown, unforeseen, or corrupted data is called intelligent. Okay? So in terms of teaching, they say if a teacher teaches everything and asks exactly that, then it's not teaching. Then it's not checking intelligence. Okay? So if he teaches something and gives something which is a little different, you have to derive it from somewhere, or you have to infer from somewhere. Then that is your mark of intelligence again. Okay? So similarly for a machine, if everything is straightforward, everything is exact, then it's not intelligent. It's an expert system at most. Okay? But if something is to be derived, okay, logically or what way, by using learning is one way of deriving that, okay, then it can be called intelligent behavior. Okay? So this business of intelligence is also very, very important because in the real world, most of the information is corrupted or it is wrong or something is always not exact. So this is again okay to understand, okay, that the system should be able to display some kind of intelligent behavior. Okay? As we go along to the experiments, we'll be looking at application of this intelligence, learning, etc., etc. Okay? So if a robot can do one or more of this, we can say it's a robot. That is more or less accepted. So by this definition, is a CNC machine a robot? So it comes back to your first question, it does not move around, right? So that is where the catch of moving around is there, okay? So a CNC machine or an NC machine doesn't move around, okay? So by that definition, it is not a machine, it's not a robot, it's a machine tool, okay? Whereas an automatic vacuum cleaner, okay? Today, Eureka Forbes has automatic vacuum cleaners where it can automatically clean, okay? It has sensors, actuators, some kind of path planning. That's a robot. Okay. Similarly, a wheelchair which has autonomous manipulation ability, that is a robot again. Why? It simply moves around. Okay. So by this three of them, we can classify whether it's a machine tool or it's not a machine tool or it's a robot. So more or less, this is accepted that if you follow this, we are able to understand what's a robot, what's not a robot. Okay. So we have, yeah. The arm moves around. That's okay, but the arm can move around. The arm is moving around, right? So if I move around, in industries, robots don't move around. It's not allowed as per industrial standard. Okay, in industrial standard, the robot has to be fixed. But the arm moves around. So in that sense, it moves around, right? Not in that sense. Not like a robotic arm moving around. Okay, that is a fixed machine. Okay. Yes, we also talk about degree of freedom that will come to, but the moving around of an NC machine and that of a robot is different. Okay, so in that sense, we use the word move around. Yeah, yeah, you can further refine it. Yeah. So this is a very general definition of these three of moving around, having some kind of sensor input output, and some kind of displaying some kind of intelligent behavior. Okay. Okay. So by this we have divided robotics, or robotics is divided into these three groups: first generation, okay, second generation, third generation, future robots. So the first generation, there are simple pick and place devices with no external sensory feedback. Okay. So the fundamental difference being there is no interaction with the environment here. Here there is interaction with the environment. For example, vision is there. There could be force torque sensors by which it is interacting. So this would be second generation. So this is 1960s. This is about 1970s. Okay. Then this is 1990s beyond. Intelligent robots, smart materials, bio-based, third generation. And then we have future robots. We have biorobots, micro, nano, cyborg, androids, etc., etc. Okay. So this is essentially how 1960s, 70s, this is third generation, 1990s, this is about 2000 and beyond, or maybe 1995 and beyond. So essentially it is the sensory interface which has gone up, okay, and some kind of intelligence has come on the system. So based on that, we are classifying the different kind of robots and proceeding. Now, the second major change that took place, the first was the invention of the microcontroller. The second is electronics became faster, smaller, and cheaper. So about 1970s, we had the invention or the development of VLSI, okay, very large scale integrated circuits. So in that integrated circuits, you could, on one board, you could put all your circuits, okay, and you could have a very small device. Okay. And that is essentially what made electronics smaller, faster, and cheaper. Okay. So all the electronics you see today in terms of mobile phone, camera, laptop, everything is the result of that VLSI only, 1970s. So electronics has become really small, it has become fast, and it has become cheap. And because of this, the use of computers everywhere also increased. Okay. And with this, we had external sensors, interaction with the environment. We had vision, advanced sensors like gyros, inclination, force, torque. We have advanced controllers like microcontrollers, DSP, FPGA, and whatnot. Then we had speech recognition, AI in that order. Okay. So about 1970s, because of this VLSI, essentially we have different new disciplines which came up, essentially because the computer became smaller and could be used more freely. Okay. So like vision, camera was there even before. Okay. It's not that camera was in 1970s. Camera was there much there before, but the computer was so big, the camera was so big that it was too expensive and too difficult to use on a robot. Okay? So the device existed, but the application did not. So the application essentially came about from here. Electronics faster, smaller, cheaper, making this 1970 onward, we have the second generation of robots, and we had the robots interacting with the environment. The third generation is essentially new materials. Okay? So about 1990s, people started wanting to make machines which are very small, micro, nano. Okay? And in that case, the conventional actuator sensors were not enough. Okay? So they had to make it smaller. Now the conventional actuator sensor, like a DC motor, cannot be made small beyond the size. It won't work. So you have to use something else, okay, as an actuator sensor. And that is where 1990s we have the smart materials-based actuators, smart materials-based sensors. Okay? So by using this material-based sensors, actuators, links, we could make very small devices. Okay? And that gave rise to the third generation of robots, which are essentially called micro, nano, then vision-based, biorobots. All this came about because of this only. Okay? So the first was microcontroller, second is VLSI, third is materials. Okay? Because of these materials, we could end up having micro robots, nano robots, vision-based, biorobots, etc., etc. Now, something to note here, something interesting here also is that about 1990s, people wanted to make small robots, micro, nano. One way was that you take a big device and you shrink it, okay, and you'll get a small device. For example, I have a lathe which is the size of this table, but I want a small lathe. Okay, why do you want a small lathe? For example, you want to cut very little. You want to cut only 0.1 mm. Okay? You want to make a very small device, and you want to cut 0.1 mm. So I make a very small lathe. Okay? Otherwise, if you want to cut 0.1 mm with a big machine, it's a waste of time, space, everything. Right? So one way is you take a big lathe, shrink it, and make it into a small lathe. Okay? And how small? Maybe, say, 20 mm square, small lathe. Okay? You're going to cut a small device. So this business of shrinking, does it actually work? Can you shrink a big machine and make it into a small machine? Can you take a big robot, shrink it, and make it into a small robot? Will it work? Why? Because you want to talk in terms of the micro domain, nano domain. For example, if you want to go inside the human body, it must be very small. So you want to make a small device. So you take a big device, shrink it, make it into a small device. Does this shrinking work always, or there is a particular scale to which the shrinking works, and beyond it, it doesn't work? Right? So that scale is called the scale effect. So you cannot take a big device, shrink it, and make it very, very small. Okay, it won't work. What won't work is, if you look at the actuators, and mainly the actuators. So if you take a big lathe which is driven by AC motor or a DC motor, okay, if you make a motor which is very small, okay, then the motor will not have power to cut anymore. Why? Because the cutting forces do not scale. So if you're cutting a big bar of steel, okay, or you're cutting a very small piece of steel, the cutting force is exactly the same. It does not scale. So material properties do not scale. So simply taking a big lathe, making it into a small lathe will not work, which means the actuator will not work. So if the actuator is not going to work, then you have to change the actuator and use something else. Okay? And that is where this business of using materials-based actuators came in. Okay? That the conventional actuators cannot be used after a particular scale, and we need to have different kind of actuators for going in the micro, nano domains. Okay? So that is where this came about. So from 2000, we have been going into different domains, very small. How small is small? For example, here we go into going inside the blood vessel and doing something. So we are already in that scale where a robot can go inside the blood vessel and do some operation and come out. Okay, so we are already in that scale, few millimeters. Okay, when we are talking of this scale, then the conventional AC motor, DC motors do not work. We have to use something else, okay, in terms, and that is where the materials-based actuators come in. All kinds of funny things have happened. Micro dentist, okay, small robots which can clean your teeth, then robotic haircut, okay. So when we talked about smart materials-based actuators, sensors, we talked about something like this. So this is a device, this is a hand, but it does not have any actuator sensors or linkages like a robotic hand, but it still behaves like a robotic hand. Okay. Now this is a materials-based, so this is basically an artificial muscle, electroactive polymer, by which the fingers are made. And it simply can contract and expand depending on. So here basically we can give it a particular charge, and depending on the charge, it will bend either this side or it will bend this side. So this is an example of a smart material-based actuator sensor system, okay, where we can make devices which are not the conventional mechanical linkages. And if you want to come to the smaller scale, then we need to go here. Why? Because these materials do not depend on scale. So I can make a very small hand, it will still work like this, okay, whereas a mechanical hand won't. Okay. There are many examples. This is an example of a bird, again, no mechanical linkages, no sensor actuator, but it works. It's material based. Okay. So again, we can make a very small device. This is the example of a snake. Okay. So it is electroactive polymer based, and it can take any shape depending on how you're actuating it, what is the control voltage you're giving, and it can give this kind of motion which no mechanical linkage can give you, right? So these are examples of material-based actuation where we can have different kind of structures, devices, simply by using different materials. These are some examples of futuristic robots. One is robots for rehabilitation, wearable robots. Okay. Then we have automatic transport. Okay. So these are for driverless buses, automatic cars. So there will be somebody who will talk about automatic cars, electrical cars. Okay. So this is again, autonomous transport is a robot in a way. happy robot, sad robot. So all kinds of things are there now. Okay. So happy robot or a sad robot, facial expressions, behavior based. Okay. People in computer science, they want to study this kind of things. Okay. Brain computer interfaces. Okay. Where you can take the brain signal and actually control a device on the other side. Okay. So these are basically interfaces between a human being and a machine. Okay. So these are some of the futuristic areas. Some of them are existing now. Driver tracking okay, for automatic cars. So this is vision-based application. So a lot of this is already there, okay, or it is actively being researched by various companies, researchers, et cetera, et cetera. Okay. So with this, we looked at the basic definitions of where robots came from, what is automation, where robots came from. We looked at that historically there were inventions, microcontrollers, then we had VLSI, then we have smart materials, based on which we have robots, the current state of what we have robots. Okay? So now let's, after this basic introduction, so this is only an introduction of the subject, let's move on to more serious talk. Okay? So we will revise some of this. Okay? So robot joints, work volume, before we move on. Okay? So some of you might have done this before, somewhere in undergraduate course, so you might have taught, so it could be a little boring, but please do bear with us. So we'll go through this very, very quickly. So a robot is made up of linkages, okay, connected by joints. So these are joints. This is a linkage. There is an end effector or a gripper, and the base is fixed. Okay? So a robot essentially has a structure like this, which is made up of linkages, connected by joints with an end effector there, and the base is fixed. Okay? It is controlled by means of a controller, which is either PC based or is microcontroller based or DSP based. So the fundamental thing is here is that there are linkages which are connected by joints. So you can have different kind of joints, and each of these joints corresponds to a degree of freedom. Okay? So when we say degree of freedom, here we essentially mean the free variable on a particular joint. Okay? So the first kind of joint that you can have is a prismatic joint. Now, what is a prismatic joint? A prismatic joint is a rectangle. This is a rectangular part which is mounted on this rectangular rod. Now, this can move up and down, but it cannot rotate. Okay, so it's very clear from this figure that this cannot rotate on this, okay, because it's rectangular. Okay, but it can move up and down. So this moving up and down is 1 degree of freedom, and it's a straight line motion. So we say this is a translating degree of freedom, where the distance is the variable distance. So the variable is the distance, which can change here, and this joint is a prismatic joint. It has degree of freedom 1. Okay? So this is a prismatic joint, degree of freedom 1. The second one is this is a revolute joint. So this is a cylindrical part which is mounted on another cylinder, and this is my axis. So again here, this can move up and down like this about this axis. So this is my axis, this is the variable. Okay? So every joint has an axis and it has a variable. Here the axis is this. Now this is a cylinder mounted on another cylinder, and there is a stopper there. The stopper is to prevent it from coming down. So this can rotate about this axis. Okay? So the variable is the variable angle there. It also has degree of freedom 1, and it can rotate about this axis, but it cannot come down. Okay? So it has degree of freedom 1, and this is a variable which is a variable angle. Okay? The second is, or the third is a cylindrical joint. In a cylindrical joint, the difference between this and this is there is no stopper here. So this fellow can slide like this, and it can also rotate. Okay? So in a cylindrical joint, it can rotate about this axis, and it can also slide up and down. So we have two variables. One is a translational variable, and one is a rotating variable. So this one has 2 degrees of freedom. Okay? So we have a prismatic joint, 1 degree of freedom, translation. Revolute joint, 1 degree of freedom, variable angle. Number 3 is cylindrical joint, 2 degrees of freedom. One is a rotating degree of freedom. This can rotate about this axis, and it can also translate. So this is one variable theta, this is the other variable x, so 2 degree of freedom. The fourth kind of joint is a spherical joint. Okay? So this fellow can move, if I fix 3 axes, x, y, and z, then this is my x, y, and z. It can rotate about this, it can rotate about that, it can rotate about that. So it's a sphere which is in this cup, which is also spherical. So this can rotate about x-axis, y-axis, z-axis, and it has 3 degrees of freedom. Okay, so this is also called a spherical joint. It is called ball and socket joint. It's called universal joint. They mean the same thing. Okay, so this has 3 degrees of freedom: 1 rotation here, 1 rotation here, and 1 rotation there. So we have these are the basic joint structures: prismatic joint, revolute joint, cylindrical joint, and spherical joint. So when you're designing a robot, the first thing that you need to decide is which joint will you use. Okay? So what is the joint structure that you're going to use? Now, it would appear that if I'm designing a robot, then the best joint would be this one. Why? Because it has 3 degrees of freedom, right? So this has the maximum degrees of freedom in one joint. So this would be a good joint to use for a robot. But if you look for all robotic applications, 99% robots are made with revolute joints. They're not made with any other kind of joints. If you have a translating motion, for example, in assembly, then you'll need a prismatic joint. Okay? So either it's prismatic or it is revolute. 99% is revolute. Okay? But if you look at biological systems, this joint, then the hip joint, knee joint, they're all this joint. Okay? So it would appear that this is a better joint because you have more degrees of freedom. Whereas in robotics, we are essentially using this joint, okay, or this joint. So what is the problem with this one? What is the problem in controlling? Why? Human beings so nice, we can control our hand so nicely. What is the difficulty? So what? More number of motors required, yes, but so what? You are getting more motion. Then why not use it? It is always required. See, our hands, we can move so nicely because this is a ball and socket joint. If it was a revolute joint, then you'll have only 1 degree of freedom. No, making is very easy these days. With rapid prototyping, you can actually make this very easily. With RP, you can make it also. You have spherical bearings which are there, right? So how it is done, this sphere is made, this one is made, then this is heated, and then this is inserted. Okay. Or you're making it in 2 parts and then they laser weld it. Or you make in rapid prototyping where there is a small connection between this, and then that small connection is just removed. So making is very easy these days. Spherical bearings are available today. Okay, bearings are there. But then what is the problem? Why? See, logically, it is giving you maximum degree of freedom. That is why biological systems are having this. Right? Our designs are optimized. And we are able to move so nicely because we have revolute joints. Well, it gives you maximum degree of freedom. So in a robot, we should be doing with this one. Why do we do with this one? No. Manipulator is designed exactly like your hand. If you look at the structure of the manipulator, it is exactly the same. Only it has less degrees of freedom because the joint is revolute. This one has more degree of freedom because this is a ball and socket joint. No, a human hand can carry much heavier load than a robot of the same weight. In fact, the weight ratio is the reverse. Okay, a robot which can carry 10 kg will weigh 50 kg, whereas a human hand which can carry 10 kg weighs only maybe 3-4 kg or 5 kg. So it is much lesser for a human hand. Human design is the best design, right? In terms of load carrying capacity, in terms of weight, self-weight. Okay, so an ant can carry 20 times its own weight. Okay, whereas a robot, a standard robot, if you want to carry 5 kg, to carry 5 kg load, the robot itself will weigh at least 30-40 kg. Okay, so it's the reversed. And it is reversed because of this only. But what is the problem? The problem is actuators, yes, but why? Why? So what? Why? See, you have 3 axes which are meeting at a point. So the moment I put 3 motors, 1 motor here, 1 motor here, 1 motor here, all the 3 shafts are intersecting now. So if this motor rotates, this will have to counteract that rotation. Otherwise, it cannot allow it to rotate. because the axes of the motors are connected now. So there are 3 axes are intersecting at a point there now. So if I put a motor here, motor here, motor here, then if I actuate this motor, this and this also has to rotate. So you will not be able to independently control them. Okay? So position control will become impossible here. Right? So although this is a good joint, position control is not possible. Why? Because the axes are intersecting there now. So corresponding to this, there is one joint and there is one motor. So it is very easy, one motor, one joint. You control one motor, one joint, fine. They are not intersecting with each other. Okay? Here, there is intersection. So you cannot control the motors independently, they are coupled now. Okay? But in a biological system, we are very easily moving our hand. How is that possible now? So the human hand, we are moving very easily, right? So we are able to do this, but a robot is not able to do this. Because human joints are not controlled by motors. That's the answer. So if you look at our actuation, they are linear actuation. So there is one muscle here, one muscle here. So this contracts, this goes up. This contracts, this goes down. So when this contracts, this fellow relaxes. So they are not interacting with one another. Okay? So these are linear actuators, where this is a rotating actuator. So there is a problem with the rotating actuators. Okay? And that is the problem, that you cannot control them independently if they are intersecting like this. And because of which biological systems have this joint, whereas robotic systems cannot have. We want to have this, but we can't. We can't control it. Okay? So we end up by having a joint which is like this. So 99% robots are revolute joint only. Okay? Again, this is a translating joint. If you want a robot which is going to move up and down in a straight line, then we use one of this. No biological system uses this. You'll never find any biological system, either animal, dog, human, having a translating joint, which means this is a very, very bad joint. It's an energy inefficient joint. Okay? So biological systems do not use this. Okay? So although this is very simple, but it has a lot of implications to understand which one is useful where and why. Now, in terms of the work volume, okay, we looked at degrees of freedom of the system, that each of the joints has a degree of freedom, and by combining different joints, you can have you can make a robotic system, right? So we understand what's the degree of freedom. We understand what's how many degrees of freedom are there on the robot. So that is the degrees of freedom. Now, how many degrees of freedom must the robot have depends on the task. So we are talking in terms of building the robot. You decided that you'll have revolute joints. There is no other way out. You can't do universal joint. So we are going to use revolute joints, or we'll use prismatic joint. Now, how many degrees of freedom it must have depends on the task. Okay? So we have a task, a very simple task here. So I have this object. I kept on the table. I want to design a robot which will pick this up from here and keep it here. Very simple task. How many degrees of freedom are required? So we are trying to understand fundamental questions here. Okay? So please do understand that there is robotics is mathematics, okay, but then it is directly correlated to the physical world. So we have to understand this very clearly. What's the degree of freedom? When something is moving, what is happening in terms of the mathematics also. So my task here is to pick up this object from here and keep it here. Very simple, right? So how many degrees of freedom the robot should have? So what is the degree of freedom? So a rigid object in space has 6 degrees of freedom. So a rigid object in space has 6 degrees of free when it's not in contact. So what are these 3 degrees of freedom? First of all, we have to define an axis now. So there is an x-axis, y-axis, and a z-axis. Okay, x, y, z as per right-hand rule. Okay, so I fix an x-axis, y-axis, and a z-axis. Now it can translate about x-axis, y-axis, z-axis because it's in free space. So it has 3 degrees of freedom, or 3 variables which are there. So x, y, and z, 3. Now this can also rotate about the x-axis. It can rotate about y-axis, and it can rotate about z-axis. So that's 3 more. So there is 3 translations, 3 rotations, that is 6. So a free object in space has 6 degrees of freedom. Okay? Now if I want to take up this object from here to here, how many degrees of freedom are involved? That will answer the question, right? So at most this object has 6. So I'm taking up the object from here and putting it here. So how many degrees of freedom are involved? Is the question clear? So this object has 6 degrees of freedom, 3 translations, 3 rotations. That is clear. Okay. Now we are saying that we want to pick it up from here and keep it here. So how many degrees of freedom are involved? You can define the axis. So let's define an axis: x axis, y axis, and z axis. Right hand rule: x axis, y axis, z axis. Okay, I have defined my axis, 3 axes. Now I'm keeping it here. I want to pick it up from here and keep it here. How many degrees of freedom are involved? Because the robot should have at least that many, if not more. Otherwise, it will not be able to do the task. So my task is to pick up this object and keep it here. So how many degrees of freedom are involved? So I fix my axis, x axis, y axis, z axis. I have kept it here. Now keeping it here is English language. What is the meaning of this mathematically? It means I have kept on my x, y plane. This is my x and y. This object being kept here means it's kept on the x, y plane. Now in the x, y plane, it can be anywhere. Right? So the CG of this object could be anywhere on this x, y plane. Now on x, y plane means 2 variables, x and y, both are variables. So it could be anywhere on this plane. So 2 variables are required. Then I need to pick it up. So this is my third one that I need, z, 3. Now going like this or going like this is again that xy only. It is just moving on the xy only. Keeping it down is in z again. So it is xyz, which is 3, right? So xy means keeping somewhere, which is 2. Moving up, moving down means z. Moving in this direction is also moving in xy only. Okay, so it is xyz. So is 3 enough or you need more? I hope it's clear that you need 3, right? Is 3 enough or do you need one more? Rotation of what? It is? So this fellow, the xy is only to one point. To catch it, this could be aligned in any direction. Right? It could be pointing in any direction. So the hand has to orient also. Okay, because it has an inclination, it has an orientation also. So that's my 4. So x, y, z, and one more, which is 4. Do you follow? So minimum you need is 4. You can't come below 4. Now this is the 4th one. Now if I had to keep it at an angle like this, then this is one more angle. So this is 5th. Now if I want to keep with an angle this side and that side also, then it's my 6th. Right? So you're depending on the task, your degrees of freedom are going up now. Right? So if you just want to keep here at some angle, then it is 4. If I want to keep at some angle like this, then it is 5. Now if I want to keep one more angle here, which is 6, right? So it is 6. So the simplest you can have is 4, 5, or 6. Now sometimes a degree of freedom can get constrained, for which you may need more than 6. For example, if you want to put your hand inside here and take something from there, so this is getting constrained, it can't move. That means 1 degree of freedom is taken off from there. That means you need to add some more. Right? So this is how we are explaining the concept of a task and a degree of freedom. Okay? Minimum is 4, 5, or 6. So general purpose is 6. Why 6? Because a body in space has 6. That's why we say it is 6. All. Yes. Yes. So you can translate and about 3 axes and rotate. Which one? Yeah, so if you don't want the other rotations, okay, then it's 4. This rotation you will need. Then 3. in this particular case, because
here no rotation is there.
this rotation is there. This could be in any angle. How will you get this angle? Because the hand must have that angle, right? So if it is like this and the hand is like this, it can't catch. It has to orient like this and then catch.
Yeah, what he means to say is if the orientation is not there, it is picked and kept in the same orientation, then probably 3 is in it.
If it has to be picked, then that picked has an orientation.
But pick and place, if they are in the same direction.
It could be in the same direction, but the robot hand still has to get that direction. Right? So this object by itself has an orientation. Because it's a rigid body, na? So it has an orientation. Let me rephrase the question. If I want to catch this object and put here, now how many do I need? Now this fellow is a cylinder. It does not have an orientation. I can catch in any orientation. Now it is 3. Got it? So this one, if I keep it like this, now it has an orientation. Now you are stuck again, right? Because you need to orient like this now. But in this case, this is a circle, cylinder. So it can take any orientation, doesn't matter, right? So that one is the orientation of the object. Okay, so it is, normally it is 4, the smallest you can get is 4. Normally robots do not have less than 4, okay, 4, 5, 6. Okay, so that is how the task and the orientation are combined. So so this answers how many degrees of freedom the robot must have. It depends on the task. Okay, so minimum is 4, 5, or 6. So we have to decide about the joints. So the joints are normally either prismatic or they are revolute or cylindrical, and the degrees of freedom that are required. Now, the area inside which the robot can position its end effector is called the work area or the work volume. Now, obviously, the job has to be inside the work volume. Okay? So if this is my hand and I want to catch something, provided I cannot move, then the job has to be inside my work volume, right? Otherwise, I can't catch it. So depending on the kind of joints we are using, the work volume will have a particular shape, right? For example, if I make only with prismatic joints, this has 3 degrees of freedom. So there is one here, it can move like this can move like this, and if I see the top view, this is the top view, the whole body can move like that. So there are 3 prismatic joints. So 1 is here, 2 is here, and 3 is there. Okay? So how do we draw the work volume or the work area? Essentially, I take the first joint, extend it completely here, and then move it backwards till there. So you get a straight line. Okay? So it's like the joint is like this. I move it backwards. This is not a prismatic joint, but it will move straight in a straight line backwards. So what you'll get is a straight line, right? So we get this straight line here for this joint. Then this joint moves from here to here. So this straight line is getting swept like this and coming down till there. Okay? So we get this area to be a square or a rectangle, right? Now, if I see the top view of this, then this square or rectangle on a plane, it will appear like a straight line when I see from here. So it will be a straight line here, right? So now when I move this like this, what will happen? Again, the same logic. This straight line is getting swept that side. So from the top view, you are getting a square or a rectangle again, depending on the lengths of this and this. So if I combine this and this, what shape will we get? You'll get a cube or a cuboid. If the lengths are all equal, it's a cube, otherwise it's a cuboid, right? So a rectangular robot has a work volume which has the shape of a cube or a cuboid. So it will be like this, like this, like this, like this. So a cube or a cuboid combining this and that together, okay? So this is having 3 degrees of freedom, revolute joints. This has 3 degrees of freedom, but it has 2 prismatic joints. So this is 1 prismatic joint, another prismatic joint, and 1 revolute joint. Okay. So in the side view, this is a prismatic joint. So this is a straight line. It can come down, so we get a square or rectangle, same as before. Now in the top view, this axis is a rotating axis. So which means my hand is like this. So the hand can do like this. Okay, so when you're seeing from the top, what you'll see is a cylinder. Okay, so from the top you're seeing a cylinder, hollow cylinder. So this part it cannot go. So this is a hollow cylinder. So if I combine this and this, what will be the shape? So what will be the shape of the volume? It will be a hollow cylinder. Inside area where the robot cannot go, that will be hollow, and this is the cylindrical part. So depending on the joint we are using, we get different shapes. Okay? So depending on the joints, we get different shapes. Now this is an articulated robot, where all the joints are revolute joints. Okay? So there are 4 revolute joints. The first joint is this one. From the top view, if I see, my hand can go like this. Okay? Which is the axis? The axis is the vertical axis. Okay? So I can go like this. So I get my vertical axis here, which is θ1. The second axis is this one, okay, which is the rotating axis. The third axis is this one, and the fourth axis is that one. Okay? So we have 1, 2, 3, 4. 4 axes. Now what will be the shape and how do we draw it? Okay? Now how we draw this is, I start off, let's consider a 2 degree of freedom system only. Okay? Suppose there are 2 links only. And my hand is like this. So there's 1 link, another link, only 2, just for simplicity, and it can move only on this plane. Okay? So it is fully stretched. So then I draw 1 arc, keeping this constant. I just move this joint, I draw 1 arc. So it is here, you get 1 arc. Then I draw this one, I get 1 more arc. Right? If you can visualize. So we get 1 arc here, and we get 1 more arc. And so I start off like this. I draw first 1 arc, then I draw the second one, 1 more arc. I get 2 arcs inside. And on the outside, when the arm is fully stretched, if I do like this, then I get 1 arc on the outside. Okay? So we have 1 arc on the outside and 2 arcs if this is 2 degrees of freedom. If it is 3 degrees of freedom, exactly the same. It is fully stretched. First this one moves, we get 1 arc. Then this one moves, we get a second arc. Then this one moves, we get a third arc. Okay? So what is the logic? You can visualize and draw very easily with for 2 degree of freedom. 2 links like this. If you draw, first you rotate this one 180 degrees, it comes down like this. You get 1 curve. Then you rotate this one, you get 1 more curve. So that means 1 curve, second curve inside. And on the outside, if I rotate the full hand like this, I get 1 curve. Okay? Now if there are 3 degrees of freedom, we get 3 curves. 2 degrees of freedom would mean 2 curves. Okay? Outside is always this plus that. Now this one is the top view. The top view, again, it can do like this. Okay? So the shape will be like this. So if I combine this shape and this shape, what will be the shape of the work volume? It will be spherical. Inside there will be some region where you cannot go, okay, here, but it's a spherical shape. Okay? So the shape of the work volume depends on the kind of joint you're using. Okay? So prismatic fellow will have cube, cuboid. This will have cylinder. This will have spherical. So our work volume is spherical. My hand can do like this and like this. So if I combine, it's a sphere. So our hand is having a spherical work volume. Okay? Okay. So after this, we have to move on to transformations. We'll start off with, I hope this part was clear, right? So please go through the basics of this. Okay? This is very, very basic. That what is a degree of freedom? How many degrees of freedom are required? How do you draw a work volume? Okay? Then we can start off with our transformations. Now in transformations, I need to go from one link to another link. So from one, the base does not move. So I'm going to assign a frame here, and from this frame, I'll go to that frame, this frame, this frame, that frame. So I basically need the transformation from this frame to this frame, then here, here, and there. Because one frame does not move, the base frame, and everything else is with respect to that frame. So I need the transformation that will take me from one frame to another frame, right? And that is what we'll have to see next, that when I'm going from frame to frame, what are the transformations involved? Okay.